Hey there, everybody. Welcome back. This is Calculus 3. We're in the final section of Chapter 12 that we're doing. We'll do 12.7 much later. This 12.6 is on motion along a curve, and let's just jump right into it. We've discussed how we can use R of t as a position vector, and we've shown how the tip traces out the path of a particle or an object over time. It's much like the laser pointer. Where you don't see the laser, you just see the dot on the wall and you can follow it. And that's like following the particle. But let's look at some physical applications that we could have. So if we look at kinematics, if R of t gives the position, then a change in position over time would give us speed. So change in position is really just distance. Distance over time is speed. But when we say a change in blank over time, that's a time derivative ddt. So we'll take ddt of R of t, our position vector, and that'll give us a vector. So it's speed with direction, and that's velocity. So we'll call it b of t. And a change in velocity or a change in speed over time is when you accelerate. So that's acceleration. And that's, again, the time derivative of velocity, which is the second derivative of position vector, and we'll call it a of t. B of t does show the speed with direction. The direction is in the tangent vector direction. The speed is the magnitude, so we can write our vector as ds dt times the tangent vector, because the magnitude of v is the magnitude of the derivative, which is ds dt. And ds dt is, remember, s is arc, so it's a change in arc length or a change in position over time. That's, again, speed. Let's take a look at an example. We have R of t. We'll just do 2 dimensions. We'll call the x component 4t to start with, and the y component will be negative 16t squared plus 64. If you set x equal to 4t, this is just 64 minus x squared. The first derivative is 4 and negative 32t, and we can find the magnitude of that right there. So 4 squared. I wrote 32 squared as negative 8 squared times 4 squared. So it's a little easier to see what factors out. We can factor out the 4 and make it 16, and then 8 squared is 64. So we're left with 1 plus 64t squared. We can pull the 16 out, as the square root of 16 is 4. That's our magnitude of v of t. And our second derivative acceleration is 0 and negative 32. So if we wanted to look at what's happening at time equals 1, our R of 1 is 4. Comma 48. I knew something was missing there. So V of 1 is, we plug in 1 into our V, and we see we get 4 and negative 32, and acceleration doesn't change, it's just 0, negative 32. So our speed at time equals 1 is 4 root 65. 65 is a little over 64, so the square root's a little over 8. And so 4 times a little over 8 would give us a little over 32 units per second. Now I plotted it, and we can see what's going on here on Desmos. This is the trajectory of 64 minus x squared. At t equals 1, my red line is my velocity vector, where the velocity is going. We know that's the tangent vector. And we have some acceleration straight down. And we're going to come back and look at this more in 12.6 part D, where I show you some of this other good stuff I've got. But for now, that's it for this section. Peace.